So welcome. Thank you for joining us for our talk today. I'd like to thank the conference organizers and OpenSSL Corp, OpenSSL Foundation for giving us the opportunity to talk here at the inaugural OpenSSL Conference here in the amazing city of Prague. It's been a blast. So today we'll be discussing the journey that SafeLogic took through building an SP-800-90-B Entropy provider for the OpenSSL 3 provider framework. As Bob mentioned, I'm J.Maynard, head of the engineering organization, and I have along with me A.Gorak, our lead implementation engineer on the project. All right, so today's roadmap includes a look at the business drivers that led us to develop a new entropy source. I'll then stop off at the design process, and we'll then take a pit stop for driver change, and Adam will come in and take a spin through the implementation phase describing a sample entropy provider. And the finale will take us through the entropy source validation process at NIST. So let's get started on the first leg of the journey. What drove us to get this done? To begin, this is not the first time that SafeLogic has dipped our toe into the entropy pool. Here's a patent first filed in 2014 and granted on January 17th, 2017. It lists SafeLogic as the assignee and is titled Managing Entropy in Computing Devices for Cryptographic Key Generation. Though it was never fully productized, it did keep us thinking about entropy throughout the years. So next, we have a strong desire to get rid of this caveat from IG 9.3.A, scenario 2B, so that's the implementation guidance from FIPS. It doesn't exactly instill a level of confidence when you read this, and it states that there's no assurance of the minimum strength of the security keys that are being used. So many software modules actually come with this caveat. So until October 1st of 2022, one had to go submit an entropy assessment report with test results along with their FIPS submission to receive what was called an ENT designation on your FIPS certificate. After this date, NIST moved to fully to the ESV testing program, where an ESV certificate is now required. So next, so next in April 2024, we started to see signals from the standards and certification bodies when LabGram 118 is dropped from NIAP. NIAP is the National Information Assurance Program. It's a US government program run by the NSA. They validate security of commercial IT products for use by the US government, and it operates under the Common Criteria Recognition Arrangement. So here I'm highlighting in red that products not yet in evaluation as of January 1st, 2025 will require entropy assessment reports that must include ESV certificates. The assumption of entropy associated with third-party claims will no longer be allowed. So that's a pretty big deal for folks out there trying to achieve common criteria. So finally, 3.5 months later in July, we see an update to the FIPS 140-3 implementation guidance. Here we have excerpts from section 9, which covers sensitive security parameter management. Section 9.3.A talks about entropy caveats and answers questions like, when is it necessary to provide entropy reports? Or what if my entropy source meets minimum requirements of 112 bits, but it does not generate enough entropy to match the strength of the SSPs required of my algorithms? So wherever you're at with your entropy source, there's a caveat for you. On July 26, 2024, we got bullet 12, which states that modules can no longer use the 2B scenario caveat. Software modules will have to have direct access to entropy sources, get entropy interface, the 1B scenario. This becomes important later. So at this point, the business is convinced that the entropy provider project is necessary, and we're a go. So now let's start to design. So what do we want in our entropy provider? We want full entropy, where every bit produced by the entropy source, you get 1 bit of usable entropy. We want enough entropy to fuel secret security parameter generation for all of our approved algorithms. We need to be performant in target applications and understand where the bottlenecks are. And while sure, we do want it to be easy for our customers to integrate this thing into our FIPS providers, we'd also like anybody running an OpenSSL 3 compatible environment to be able to drop this thing in and achieve their desired security posture and compliance requirements. So why not build an OpenSSL 3 compatible provider capable of delivering entropy to all loaded FIPS providers? So here we can see what that looks like as part of the standard OpenSSL 3 architecture. And so first, we love the OpenSSL 3 provider framework design. It is the de facto framework for providing algorithmic cryptographic agility in C-based applications. And next, we have customers that we need to support across many versions of the OpenSSL 3 ecosystem. So with an OpenSSL 3x compatible provider, our customers can essentially BYOE, bring your own entropy to your application, regardless of which OpenSSL version you're on. And so finally, my team has experience here. We're probably one of the only teams I'm aware of who ever embedded one of the old V2 canisters into the V3 provider framework. Since our FIPS canister was 140-2 validated already, we were able to migrate many of our customers early to OpenSSL 3 APIs and provide FIPS TLS 1.3 capabilities, while others were taking the built-in provider through a new 18-month process in queue. We should know, we also took a 140-3 provider we built in 2023 through that same queue. Anybody have an idea of how long it took us to get through it? That's right, we received that just recently, earlier this year, so over a year and a half. So let's take a closer look at scenario 1B. The top orange arrow highlights that the FIPS module will need direct access to the entropy source's getEntropy API. The example given here utilizes an SP-800-90-B entropy source, and the rest of the verbiage relates to which caveat you might need based on your minimum entropy. So we won't worry about that now. Adam will get into that a bit later. So you might ask, how do we get direct access to the getEntropy API required by scenario 1B across providers? So additional comment 10 of IG 9.3.A allows for the use of callbacks to obtain the entropy as long as the callback path allows for direct access to the getEntropy interface. So here on the left, we have a FIPS provider that has a function pointer that needs to be set at initialization to the preferred getEntropy API. The fetching capability provided as a common service to all is the real hero here. We use fetching to retrieve the pointer to the concrete location of the getEntropy API in the configured crypto-comply entropy provider, and voila, you have direct access. And there you have it. The lab is, oh, I must have skipped something here. Yeah, so now that we have a good design, what does our lab of record think of it? So there you go. Looks good to me, right? So we've got the thumbs up. Now let's go build it. So I'd like to now bring Adam to the mic to take us through the implementation leg of this journey.
Okay.
Thanks, Adam.
Thank you, Jake. So I'm A.Gorak, Senior Software Engineer at SafeLogic. I would like to give you a deeper view of the OpenSSL provider framework. The provider framework allows cryptographic algorithms to be implemented as a separate pluggable modules called providers. Instead of having algorithms hard-coded in the OpenSSL core library, we can dynamically load them from providers. So it makes easier to replace, update, or even replace or extend some crypto functionality. Okay, here are the most important parts of this architecture. We have EAVP API, which is an application or user interface that is used to talk to the OpenSSL. Of course, we have OpenSSL Core, which contains context data and all its common data types. We've got one or more provider instances, and every provider is supposed to have an init method that is entry point and a way of exchanging functions between the core and the provider. Here's a different view of the interaction between the application and the provider, and its description. The life cycle of the provider instance in the core is as follows. First, the application triggers the provider load. So the OpenSSL core tries to load the provider file, and for this, the OpenSSL core calls an operating system loader to load a shared object or DLL. On Linux, it's a DLOpen function. On Windows, it's a load library function. So once the provider is loaded, the core locates the init function and tries to call it. In the init function, the provider advertises its algorithms along with their names, properties, and these get registered in the library context algorithm store. And now, since then, the algorithms can be used by the application, right? So let's try to create, build, and install and use an example, very simple provider, just to show you how it's simple and how it can easily be extended. So what needs to be done? Of course, first we need to have some C implementation. We need to compile it and produce a file that can later be loaded by the core. Of course, it needs to be configured. The installation is just a matter of placement the provider file in a directory where the core locates the providers. And that's basically all. I will show you. This slide presents crucial parts of the provider unit file. First of all, we've got the init function. In our case, this function is very simple. It just sets the reference to the provider dispatch table to the out parameter, and that's it. In the dispatch table, we have a reference to the query function. In the query functions indicates the operations that are supported by operator. In our case, it's just a run operation. The query function also returns a reference to the algorithm table, and in the algorithm table, we have algorithm name, algorithm properties here, and a reference to the algorithm dispatch table. And this table is the actual definition of the concrete functions that implement a particular operation. In our case, it's a run operation. And we are interested in the get entropy function, get seed function in this case, because this simple provider is going to provide a kind of entropy. Yeah. All right. So as I mentioned, there was an init function. The init function is quite important. It has an input parameters and output parameters. The input parameters is handler. It's basically a pointer to the core, and it needs to be passed whenever the provider calls the core functions. The in is an array of functions exported by the core. The output parameters are out, something that we need to populate to the provider dispatch table, and an optional parameter provider context. It can be created if provider wants to keep and maintain its state, right? And the dispatch table. It's an array of function pointers paired with function identifiers paired with function pointers. Yeah, so it defines which operations are available and how to call them. This mechanism is used both ways, by provider and by the core. It's a kind of function registry shared between the OpenSSL core and the provider. Right, and this diagram shows how the OpenSSL core discovers functions related with, in our case, run operation. Most of this function needs to be implemented and provided if we want our provider is recognized and used as a seed source. So that's why we select this type of functions. Yeah, and the important function, myEntropy get seed function, is the actual implementation of the getEntropy conceptual interface. Okay, and finally we've got the implementation of the getSeed function. As you can see, it's very simple. First of all, we've got some debug line, printf, and we create a buffer of required length. We populate it with system getEntropy call, and that's it basically. As you can see, the compilation of this file is also quite simple, quite straightforward. We produce a file, we create a file directly in the OpenSSL modules, and the content of the provider file, this simple one, is also quite simple. It's, as you can see, there is one public symbol, the provider init, the entry point, and all other symbols are functions and variables are local. Yep. Yeah.
Is that the Linux getEntropy call, or is that your own implementation?
This function it's a system call.
Yeah, I know. That can fail.
Sorry?
That can fail. No, it can fail.
It can fail, yeah.
Yeah.
But this is just an example.
Oh, okay. So
this is just
it's
not.
There is no error checking in this code, and you are potentially passing no entropy out via this operation.
Yeah, but also when you can see on this init function, it's also very simple, and it does not produce the result because this is, the most simplified version of the provider that one can create, but the provider that can be actually used and works. So. Okay, so let's try to configure it and configure this provider and test it. The configuration is also very simple. This provider does not have any specific properties, so the only thing that we need to do is we need to add its name to the list of providers that should be loaded, and we need to instruct the OpenSSL to activate it on loading. Additionally, we set this provider to be default seed source for the OpenSSL. In this case, we use a custom installation of the OpenSSL, so we need to additionally set few environment variables. And as you can see, when trying to generate an RSA key, we get our custom debug line, and then the key follows. Yeah. Okay, our simple example entropy provider probably does not meet the SP-800-90-B standard requirements. So the question is, what is the compliant entropy source then? It needs to be rigorously tested. It has continuous monitoring of the entropy quality. It's a statistically validated source of randomness that guarantees true entropy for cryptographic use. And of course, it must provide a measurable amount of unpredictability per output symbol. It needs to have a documented design. In general, it's well documented. And of course, primarily, it needs to provide or implement certain interfaces, like conceptual interfaces. The getEntropy is a mandatory interface. The other two are optional, and they are used during the lab time validation and design. Okay, this is a simplified architecture of crypto-comply entropy provider. This architecture corresponds to the overall design of the entropy source shown on the previous slide, and it's based on the jitter entropy library, and it's wrapped with the OpenSSL provider. The seed source generate function is the implementation of getEntropy conceptual interface. This function in turn uses gent read entropy function to fetch the entropy data. Okay, this slide could be skipped, but okay, quickly. Okay, so what happens in the init function of our provider. We get some callback functions. We create the provider context. In the provider context, when the provider context is created, we also create a default backend seed source, and we get the provider properties from the configuration. We perform internal integrity tests, and also we need to set the provider dispatch table or set in the output parameter. Right, how we are using the crypto-comply entropy provider in our crypto-comply FIPS provider. Of course, the entropy provider needs to be configured and present in the running context. So the initialization of crypto-comply FIPS provider fails if the entropy provider is not available or it's misfunctioning. For example, if it's in an error state or cannot generate the required entropy. Okay, the FIPS module uses crypto-comply entropy default seed source context containing entropy collector and its generate function to actually provide the entropy to the OSSL prof get entropy, which in turn is provided to the other parts of the provider, of the FIPS provider. Fetching the entropy in crypto-comply FIPS module happens directly between the FIPS provider and the entropy provider. Okay, and our provider can also be used globally as a default OpenSSL entropy source. In this case, we need to set the seed property of the random configuration to this name crypto-comply entropy seed source. Okay, and configuration of the provider is placed in its dedicated file, and this specific file is included in the main OpenSSL configuration. The configuration has basically three properties. One is activates a common property recognized by the core. The module MAC, which is an HMAC value that is used during the internal test of the provider, and force internal timer is an optional flag that is passed to the jitter entropy library. Right. Here's this slide demonstrates how the provider is seen in the OpenSSL when it's properly configured. So first of all, it's seen on a list of active provider, and additionally, if it's set as a default seed source, it can also be it should also be listed on the list of random generators. Yeah, and the validation of SP-800-90-B compliant entropy source requires several tests to be performed for each supported operating environment. The most important ones are modeling of noise source and estimating the minimum entropy. Also gathering entropy data sets and validating them with entropy assessment toolkit. These data sets are generated under realistic conditions in a target operating systems. All additional cryptographic algorithms needs also be tested. In our case, it was SHA-3 algorithm that is used for conditioning of the entropy data, of the noise entropy data. Okay. The validation of the compliant entropy source also requires preparation of certain documentation. The most important ones are EAR, which is a central document. It contains a description of the noise source. It contains entropy data sets, statistical results, a description of health testing, and description of operational procedures. The second important document is a PUD. It's a kind of public user guide document that includes identification information, entropy source description, operational parameters, and integration details, and some references. All right, so thank you. Now I will hand it back to Jake so he can talk about finishing it up at NIST.
Thank you, Adam. Awesome job, buddy. All right, so here's a timeline view of how the project played out. In July of 2024, we greenlit the project internally. By the end of September, we had scoped and resourced the project and were beginning to implement. By the end of December, we had completed implementation, raw data collection, CAVP testing for the SHA conditioning component, and we're in the CMVP queue just in time for the holidays. We don't hear much in January, but around middle of Feb, we get confirmation that we're in review. In March, we have a round of comments, and in April, we get the great news. We're validated. So to put it simply, this is roughly a 10-month project that took 4 separate specialists internally, if you include the FIPS operations team that collaborated with us on the document submission. There's also our testing laboratory, the NIST ESV testing itself, and then generating the documentation submission package. Now add that on top of your FIPS module project, and this is the new reality facing those heading to the CMVP post-2025. You can find our certificate in the NIST ESV search. Here you can see it's E241. You can also see the 16 OEs that we physically tested. And if you click on the link to the E241, as Adam said, you can access the public use document, which contains information for usage and some of the min entropy information. So with that, definitely like to give a special shout out to Lightship Security. That was our testing laboratory. Also like to thank Stefan Mueller for making himself highly available to us. And anytime we found an issue, he was very quick to resolve that. So with that, be happy to take any questions.
So basically wrapping the libc/Linux kernel or whatever operating system you're operating on, how much tied is the certificate to the underlying operating system? That's my first question. So
Good question.
in instance, what happens if you swap out libc or the Linux kernel to different version? The second question is, to what lens have you had to go through to obtain the validation in terms of what is actually happening inside the kernel?
You want to handle that, Adam? I'm not sure I understood the first question. So if
the first question, sorry. So what happened? In other words, is the validation still? Is the certificate still valid if you swap out the Linux kernel version or the libc?
So the operating environments that we test against are the ones that are the validation are geared for. So ultimately, if you change any component within that operating environment, it's no longer the same operating environment, right? If I understood your question correctly.
Also, it's important to note that it's not a kernel-based implementation. It's a user-space implementation, because you have mentioned something about the kernel.
Yeah.
Yeah, to be clear there, to reiterate from someone who's also suffered with this, you are, the device itself is certified, their thing is not in kernel, but your entire operating environment that you have decided to use, you must also certify in addition to this. So it's not just their stuff, it's your whole thing. Now they've pre-certified certain environments. If you want to use something different, you would have to take their certification for their device, send your entire environment to your lab, and get your lab to certify it.
Typically, if you have the same operating system, same CPU architecture, that's like how OE is defined, so you can use it on those. And yes, with ESV, there's usually, or a lot of the time, there's need to add additional operating environments, which is completely doable and something that's, can be done.
And that's my boss, Evgeny. So thank you, Evgeny, for adding to that.
Yeah, so my question is around going back to the FIPS provider has an exception in it around the key material in the entropy source. So now if you tie the FIPS provider to the entropy provider that you have, can you bring the FIPS provider back to certification and get rid of that exception? And is that kind of the pattern that you should use for getting FIPS certification of like providers that are providing cryptographic algorithms?
Following?
Yeah, I'm not
Makes
sure I
sense.
followed the question,
Okay,
man.
yeah. So the FIPS provider has an exception in it that it's not generating random or entropy. It's not a guaranteed entropy resource. And the random data that's being used, say for the keys, you can't guarantee that. The FIPS, the entropy provider that you just created, guarantees a random entropy source.
Yeah.
Right.
You can tie those two together with a fetching characteristic that you had that's external to the provider.
Yep.
So now, can you bind that FIPS provider to your entropy and now bring the FIPS provider for certification and get rid of that exception that's now in the certificate for the FIPS provider?
Yeah, so that's the whole point of doing that, right? So once you've got direct access to the Get Entropy API, you're meeting min entropy requirements, the caveat's no longer necessary.
And so from a FIPS or a NIST perspective, they're happy enough that you've bound that FIPS provider to your entropy. Okay.
Yep,
So
absolutely.
this becomes the pattern that should be used going forward is have a provider for entropy that gives you true entropy source, and then you can bind your FIPS provider to that entropy source.
Absolutely.
Okay.
Yep. The two become very married.
Thanks, Adam, for the gentle introduction, how the simple provider looks like and how it's called, etc. Also how it's configured with OpenSSL use as a default random number generator. Recently, a colleague of mine had a down-to-earth problem. When your application wants to choose between several sources of randomness, what if you don't want to have it as a default provider? What do you want to switch between various sources? How you would address them from the OpenSSL API when a application wants to decide which of them to choose for each operation?
The application, you mean? I mean, this is. I mean, this can be achieved first of all by defining the properties of the provider. Yeah. So when selecting the provider, first of all, you can filter out what you are interested in. When certain provider, like providing the entropy or randomness is available in the context and certain properties are matched, then this provider can be used in the application. I think when both application and this provider is in the context.
Mm-hmm. So you would specify certain properties that could uniquely identify your provider and to be sure that this one is used.
Yeah.
Okay, thanks.
But there is a difference between the really simple example provider that I have shown at the beginning, where there was nothing about specifying properties, etc. So it was just enough to specify. In order to use it, we just added or set it as a default seed source in a seed random configuration. While there is a bit different implementation in our provider, of course, which is where we use the properties to select, etc., etc.
Thanks.
I'll give you one more as a bonus.
Oh boy, thank you, Bob.
Given that I could probably take my OpenSSL and configure your device as either my default entropy source or as an entropy source I can select when I know I'm using my FIPS module, are there performance limits that if I was a very large thing would make it advantageous to me that if I was using a combination of FIPS approved operations that required entropy and non-FIPS operations that just need entropy, should I be selecting between your device and the default entropy provider?
It's a very good question. Yeah, you'd probably, for the non-FIPS operations, would prefer not to go to the 90B entropy source. It does take more resources to generate true entropy, of course.
Yeah.
So thank you for the question.
If that's it, nobody else? Okay. Thank you very much, guys.
Appreciate you all. Thank you for your attendance.